bias correction.
Hi everyone. So it's nice to be here. I am currently starting to work my way into privacy. I've been really delving into it over the past couple of months. My background is statistics, and more specifically robust statistics. And so when I arrived at Penn State, I saw some connections between, or possible connections between, robust statistics and privacy. And so I started working on some ideas, and this is more or less an overview of these ideas and some possible preliminary results that could help improve the usefulness or statistical accuracy of the outputs. So the idea are, well, the connections between robust statistics and differential privacy, you all know, are not new. There's the first, to my knowledge, first paper that underlined this link was Dworkin and Lay, where they use robust statistics as a basis for a proposed test release algorithm. Then Lay focuses on M estimators for using perturbed data, and more recent one was Chowdhury and Su, who use a robustness measure to study the convergence rates of differentially private outputs towards, in terms of approximations to statistics. Along this line, this talk aims at understanding if some tools that exist in robust statistics and in bias correction can help in terms of preserving differential privacy, let's say pure differential privacy, and improve at the same time improve the statistical accuracy of these differentially private outputs. So the first thing is, the first idea is using M estimation as Lay did. So the idea is we define an estimator that we'll generally call T, and we define it as an M estimator, which we'll see later what an M estimator is, and apply a bounded function to it, which is something that's commonly done in the robust literature, robust statistics. And thanks to this bound, we can deliver results. There's a natural result in terms of the sensitivity of the resulting estimator. And that can, of course, be helpful in determining the amount of noise to be added for the differentially private output. And therefore, there can be a kind of trade-off between the bound you put on your M estimator and the accuracy of your differentially private output. A second idea that I wanted to go or test today was understanding how some recent ideas from statistics in terms of bias correction can help improving the statistical accuracy of differentially private outputs. So the first idea was an idea that was lying around since 1995. It's called iterative bootstrap. And that was proposed by Cook. And recently, a paper has shown that this method can correct finite sample and asymptotic bias exactly in many cases under certain conditions. And therefore, this procedure can eventually be used to correct the bias of biased differentially private releases. And so that's one method that I will be actually using today within the results I'll be discussing. A second one is very much related to the talk given earlier on confidence intervals. So what kind of inference? So once I've released my private output, how can I perform tests to understand or retrieve information regarding parameters or information from my original data? And this is another recent approach that allows to deliver an inference framework at very little cost in terms of mathematical developments. So, given that this is these are the goals, so I'll briefly introduce what robust statistics is from my perspective. So, discussing with some of you, what came out is that my background in robustness is not necessarily the same kind of robustness that maybe is known within differential privacy or as well in other areas of statistics. So I'll first underline what my background and my perception of robust statistics is. Then I'll be giving a brief idea of what these, what I call post-processing mechanisms, so bias correction and switch Z estimation for inference. And then I'll just give some results of a very simple simulation setting where I use objective perturbation for differential privacy and analyze how the robust solutions with the iterative bootstrap can help improve the statistical accuracy of the outputs. And then conclusions and possible future work. Okay, so if there are any questions, please stop me whenever you want. Okay, so the background that I come from for robust statistics is this one. What you assume, so maybe one way to look at it is, say you want to generate some synthetic data, and you have a generating model for your synthetic data. And this can be univariate or multivariate data. Okay, and so let's say that this model we call f theta, where theta is the parameter of interest that defines your model. So what robustness says, or robust statistics says, is that this model is at best an approximation of reality. Okay, so it's all models are wrong, but some are useful. So assuming that my data comes from this model is an approximation. So how, and what we observe in reality is a contaminated version of this model that we assume. So robustness starts from this setting saying, okay, my data comes from, yes, it comes from the model f theta, but a certain proportion of it, which is small, delta, comes from a certain other distribution or other model G. Now, G, for purposes of robust statistics, is left unspecified. We don't want to specify what G is. We're just interested in our data generating model f theta, which is contaminated with G. Okay, so we're interested in the parameter theta. Okay, so given that we don't want to specify what G is, the issue is how do we deal or identify the observations or so-called outliers that come from this distribution, because in some way we'd like to be able to identify them, and therefore if we manage to identify them we can get rid of them and at that point perform normal analysis on data that comes from f theta. Problem is, in many cases it's very hard to identify outliers, so it's especially in highly structured data or high dimensional data, you don't exactly know what an outlier is. And if you perform a certain kind of removal of your outliers, this can highly impact the inference and estimation and inference procedure you perform afterwards. So when you perform tests based on your estimations, these could be very wrong. So the idea of robust statistics is, okay, I want to study and reduce the impact of outliers on my estimation procedure. So whatever statistic I'm computing on my data, I want to reduce the impact of outliers on it. And once I've done this, I want to have an appropriate framework where I can have my point estimate and I can perform my inference, testing whether a certain hypothesis about my data is true or not. Okay. So to do that, robust statistics proposes some measures, and it measures how much a certain statistic or certain operation you do on your data, how much it is impacted by outliers. So this connection was already made in Dwork and in later papers saying what is the impact of a data point that changes on the operation I make, so the algorithm or estimator. So in order to study this impact, robust statistics just uses or defines an estimator or a statistic, whatever you compute, as a functional t. So an estimator t can be expressed as a functional, saying that it depends on my underlying distribution f through the data x. So you can say that my estimator is a function of my empirical distribution function, f of n. And for example, the sample mean can be expressed as a functional this way. So I just say that the sample mean is this functional here. Okay, so it's just a way to express estimators in a way that can be studied, as we'll see later on in the robust framework. So if there are any questions, please go ahead. First measure that is used and which starts to indicate the proximity, eventual proximity of robustness and privacy is the sensitivity curve. So this function is defined as follows. So suppose we have n-1 fixed observations that we put into a univariate setting, okay? So we put all these n-1 observations into this vector. And we add an nth observation, which we call x0, and this observation is allowed to move along the entire real line. So the sensitivity curve is defined as this standardized difference between the functional or estimator or algorithm applied to the n-1 vector with x0, with the estimator algorithm applied to only the xn-1. Okay, so if you define what the estimator is, for example, the sample mean has this sensitivity curve. And so basically what that means is this sensitivity curve is directly proportional to x0, and therefore if x0 goes to infinity, so does my sensitivity curve. So in this case, the sample mean for this version of this robustness measure is unbounded. So the measure that's actually very much used in robust statistics is the influence function, which is basically, in very loosely speaking, an asymptotic version. So when n goes to infinity, it's an asymptotic version of the sensitivity curve. So basically, we have our contamination model, except that in this case, we specify that G is a point mass distribution in x0. So x0 is this point that can move along the entire real line, and delta x0 is the probability mass, the point mass distribution in that point. So we said earlier that robustness doesn't want to specify what that contamination is, but it does so in this case because it was proven that the maximum bias that an estimator can undergo in terms of contamination is exactly the point mass. So the influence function is basically studying the maximal possible influence of or bias induced by an outlying observation. Okay, and so based on this definition, the influence function is expressed as this Gatto derivative with respect to the contamination distribution, where this implies limits from the right. Okay, so delta is going to 0 from the right. And if you just do the same as before, sample mean, for example, the influence function is, not surprisingly, this guy here. And of course, we can see mu is the actual location parameter that we want to estimate, and x0 is, which is fixed, and x0 is allowed to vary. So sensitivity curve, the influence function of the mean is unbounded.
So when you apply t to a distribution, and you said this already, you're taking it as some, is t, how is t?
So t is, so an estimator, or you can see as being a function of your data. So the mean, for example, is a function of your data which is itself a function of an underlying distribution. So let's say they come from a normal, t can be seen as a function of the normal distribution.
The empirical distribution.
In this case, it's the empirical distribution. So it's based on the data, based on the empirical distribution, and it converges towards
right,
the true one.
That's what I was going to ask. There's an assumed connection between how it behaves on finite samples and how it behaves on sort of when the argument is like a general distribution, that I guess is some kind of continuity condition on the...
Yes, exactly. So you're assuming that that you're, well, that's again, that's a kind of discussion on the properties of your estimator. So if it's the sample mean, then we know that T of Fn converges to T of F, and therefore it's a consistent estimate and so on.
Appropriate moments.
Yeah, whatever. Exactly. So we're not specifying whether or not this is a consistent estimator or not. We're just saying that we can express it as a function of my underlying distribution through my data. And we're not assuming, for the moment, we're not assuming anything. Once we express what functional it is, we can study its properties and understand whether it's consistent with respect to a certain assumption. So yeah. I don't know if I answered the question there.
Yeah, no, that's fine.
Okay. Okay, so influence function. So in this case, the influence function is a measure that's commonly used in robust statistics to understand if to define whether an estimator or whether a certain functional is robust or not. And so another measure, and this is the last one, is the gross error sensitivity, which is simply the supremum in x0 of my influence function. And so an estimator, or T, is considered or defined as being robust if its influence function is bounded. And therefore, which implies that also my gross error sensitivity is bounded. So this measure, this gross error sensitivity, was actually used in a paper of Chowdhury and Su in 2012 as a way to study the convergence rate of differentially private approximations to estimators. So that's the connection. Well, that's one of the connections to differential privacy. So basically, this is measuring. You can see this as measuring the maximum amount of influence that one observation can have on my estimator or interpreter as being algorithm. Okay, so it's basically. So given that I'm new to privacy, I'm supposing it's related to the concept of the sensitivity of the algorithm. Yes?
We should think about this as local sensitivity rather than global.
So I'm guessing, well,
this is for fixed f theta.
Yes, this is for fixed f theta. So if it corresponds, I guess it's. I think it corresponds to the definition of local sensitivity and privacy.
The expectation of that. But
yeah. Okay. So that's more or less the framework we're in. So the background of robust statistics. Now, the idea is, okay, for robust statistics, we want to define functionals T, statistics, or algorithms that respect this condition, i.e. whose influence function is bounded. Okay. So one of the main tools used for this purpose is the framework of M estimation. So let us define the functional T as being an M estimator. So, and defined as the minimization of this convex problem. So we want to find the parameter theta, which is of interest, based on minimizing this convex function. Okay, so this is a very general expression. Many problems can be written in this way, as we'll see later on, and as you probably already know. And we can express this M estimator, and it's often used in robustness to express it in a different way, is simply to define it as the solution zero of a certain score function psi, where psi is the derivative of my convex function with respect to the parameter of interest. Okay, so basically we either find theta that minimizes rho, or we find theta that makes this argument zero. So if we go to a standard statistical background, the MLE, the maximum likelihood estimator, can be expressed as an M estimator. So you're assuming a distribution for your data where small f represents the density function of your data and defined by the parameter theta that you're interested in. Take the log of that likelihood function, negative, and you minimize that. So that's maximum likelihood estimation. So that in that case, the rho function is this function here, and alternatively, you can express it as the arg0 of the derivative with respect to theta of this function here. Okay, so in this case, we of course, if theta has dimension p larger than 1, this is a system of score functions. Okay, and you need to find the solution 0 to all of them. Now, another example which is what we'll be looking at in the simulation results. Well, the preliminary simulation results is this location parameter problem. So, say we wanted to find our distribution is f and it's centered around theta. Say we wanted to find theta. Well, to find theta, and we can define it as an M estimator where we just say, okay, it's rho of x minus theta, or alternatively as the solution is 0. And so if we define rho as being y squared over 2, then this just goes back down to finding the sample mean for a normal distribution. If we define rho as being the absolute function, then this corresponds to the median. Okay. So it's a generalization of certain estimators. So given this, what happens with the properties of these M estimators with respect to the robustness measures defined earlier? Well, remember we wanted to bound the influence function, which corresponds to bounding some way the local sensitivity. Well, for an M estimator, the influence function is defined this way, where this term b is simply a constant, an expectation which is based on the parameter. So, and this part is the only part that depends on my point mass distribution x0. And so we can see that the influence function of an M estimator is directly proportional to this psi function, the score function. Okay, so if we have a bounded score function, our M estimator is robust, and therefore its sensitivity is bounded. So that's basically robust statistics make good use of M estimation, since they use bounded functions for this psi in order to bound them. Okay, so what are the solutions? So there are various functions that are used to bound this score function. So if we go back here, we could just say that this guy is x minus theta squared, and therefore here we just have 2 times x minus theta as being the score function. So what do? 2x minus theta is not bounded, so we apply a bounded function to it because we know that the expectation of my score function is 0. So I know that I want to find a solution in a proximity of 0. Okay, so the idea, for example, one commonly used bounded function is Huber's, the family of Huber functions. And it's defined in this manner. So within a certain distance k of my solution, which is in 0, I define the score, the rho function as being the same as my, so it's basically the quadratic solution of least square problem, and then it becomes linear. So what does that mean? Its derivative is bounded, because it's bounded between k and minus k. Okay, so if this tuning constant k, which determines where we want to cut around 0, when it goes to infinity, this is simply corresponds to the sample mean. If it goes to 0, then we have the median. Okay, and so this is just a representation of these two functions. So this is the convex function rho that we want to minimize. So it's quadratic, and then it becomes linear outside of k. And then, so if k goes to infinity, all this function just becomes quadratic, and so that just becomes the sample mean. If this goes to 0, it becomes linear, and so we have an L1 problem. And so in this case, as you can see, the derivative is bounded between these two values determined by k. So the idea is we apply a bounded function in order to bound the sensitivity and the inference function of my estimator or my algorithm. Okay, so given this, the issue with doing this is the following. Your score function, let's take this guy. So if we're estimating a location parameter, we can say, okay, my score function is 2 times x minus theta, and theta is what I want to estimate. So I want to find theta that minimizes this sum. Okay. The problem is, if I apply the weight I saw here, it's a symmetric weight. So basically, what I'm doing is, if x comes from an asymmetric distribution, I'm basically cutting off values that actually are quite informative. And so I'm cutting around the center and throwing away important information on one side. So what this does is introduce bias in robust estimation. So often M estimators are defined through a bounded function plus a correction term to remove the bias. And so this is just stating that this correction term is often needed according to the problem you have. But this is a problem that is often quite complicated to solve because it depends on the assumed underlying distribution for your data, and therefore it's on a case-by-case basis. Okay. So one solution that is recently proposed, and now I come to the post-processing mechanisms, is the following. So we have, let's say we have an estimator or an algorithm T, and we denote it as follows, as pi hat, which depends on the data, which depends on my true underlying parameter. Theta, I'll call that theta 0, my true parameter. Okay. And so, of course, it's not an explicit function of this. We don't observe theta 0, but there's a link between the auxiliary estimator and theta 0. So basically, pi hat can be my robust function, my robust score function bounded, applied to an exponential distribution, which will therefore give a biased estimator of the mean. So, okay, so this is a biased estimator. I'd like to correct it, i.e. I'd like to find an unbiased solution to theta 0. Okay, so the idea comes from this iterative bootstrap, where basically I define, this is the auxiliary estimator computed on the sample. So say I use the median to estimate the expectation of a distribution. So if that distribution is symmetric, the median is an unbiased estimator. If it's asymmetric, it's biased. So assume that this is the median. Okay, and I want to, and theta represents the expectation of my distribution. So this is going to be biased, given that this distribution is asymmetric. So what I do is I take what I had from the data, and then I simulate from the distribution I assume for my data. So say I'm saying my data is exponential. I simulate from that distribution using a parameter theta k minus 1. So this is going to be, as the name says, iterative. So it's the previous solution. And basically, I'm going to simulate based on the previous solution and compute my auxiliary estimator. And then, basically, what I'm doing is trying to find the theta that makes these guys as close as possible. And I do that in an iterative fashion. Okay? And the starting pi can be my initial biased pi. So I can start with a median, plug it here, then I simulate from an exponential distribution whose mean, whose expectation is going to be equal to my previous median. Simulate from that and compute my median again. So this is the expectation of my median, given that I'm simulating from what it should be estimating. Do that, and then I basically continue doing it until I converge. So until my steps are within a certain distance. And it is shown that this procedure can correct finite sample and asymptotic bias under very general conditions. So in the privacy setting, my guess is that one can use a differentially private biased output. So often when you introduce noise, you can bias the resulting outputs. And therefore, in order to improve the accuracy from that output, one can use this mechanism. And indeed, I use it within the simulation study we'll see in a few moments. Another procedure, which I won't go into details about, is the inference procedure. So you can correct the bias, and now how do you perform tests on your data? If I'm interested to perform tests on my differentially private outputs, how can I perform the inference? Well, according to the type of problem or differentially private algorithm, this can be quite complex to do. So already in assuming that I have resolved Gaussian data and adding noise, then it's already quite complicated. This algorithm is basically based on indirect inference, which is what inspires the iterative bootstrap. And basically by putting h equals 1 and then repeating this procedure b times, what you get is a distribution of my estimator. And it's some way, it has very similar properties to approximate Bayesian computing. So this is a very low-cost inference method that can be used. I haven't used it for these preliminary results, but this is a future avenue of investigation. Yes?
In this process, you're not trying to re-weight in any way the sample points you have, because once you did one iteration, even now you have some estimation about which ones are the inliers and outliers. It's for each pair point, it's either this or that. So they're like equivalent algorithm like IRLS and stuff that try to achieve a similar thing via.
Yes. So there is the iteratively. Well, for example, robust statistics. To solve many of these score functions, for example, linear regression, they use the iteratively reweighted least squares problem. So at each iteration, you weight your observations, you compute your estimate again, and then until convergence. That's true. So in this case, what that does, it finds you a point estimate. So say I want my betas for a certain problem, so for a linear regression problem. Well, that gives you a solution. So it gives you the points, the values. But now say I am a researcher and I want to understand if that value actually contributes to explaining my data. So should I keep this variable in my data? Should I use it or not? I need a distribution for my betas, right? So that procedure, and it's exactly what is used in robust statistics, that gives you the points. Now I need to understand how they behave to understand if it can be close to 0 or not. And so this procedure, that is a pretty much quite simple scenario, but there can be very complex settings where this guy is analytically intractable. And so this procedure allows you to give you a distribution for my estimator at a very, a little computational cost. Okay, so this is another avenue of research that can be done. Yeah.
So this sort of setup requires that you be recovering like a generative model for the data.
Exactly. Yeah. So so that's one of the possible limitations that I wanted to underline regarding this philosophy of robust statistics. So you're always assuming, in general, that there's a generative model for your data.
Well, I guess I meant as opposed to, say, a regression problem, where you're recovering just sort of some part of the generative model, like namely the the link between the
so if you're saying
thing you're trying to predict and the dependent variables.
So basically, well, for the betas, so you're saying for a regression problem, my interest is finding the parameters, the betas.
Say the coefficients.
The coefficients.
Like, yeah, for linear regression, you'd be interested in the coefficients. But then it's not clear this type of how to apply this type of approach, right?
So
because you can't. You don't have a generative model for the entire data set. Just
yes,
sort of like
exactly. So that's exactly what I meant is the limitation of this is that for robust statistics you're assuming, for example, that your residuals. So you have your betas plus an error, right? And that error has a certain parametric distribution. So say it's a normal, it's a Gaussian, then it has mean x beta and variance sigma squared. So the idea is, in that case, now you can work with this. So say you use simple linear regression to estimate the betas from a logistic regression, where you're trying to classify between 0 and 1. This procedure can allow to correct the bias because you're not solving a linear equation there. So it's basically maybe you can use a problem, but of course you have to have a fully specified parametric setting. So you're estimating a model, including your noise, because that's what allows you to generate, and then you can debias it.
In a normal linear regression, you do have a generative model. In a normal linear regression, you're assuming that your y given the axis is normally distributed, which is the equivalent to assuming the error has a normal distribution. So there is a generative distribution in certain type of regression models.
But I guess you're assuming that you have sort of. I'm thinking maybe I'll save my question for later. I'm thinking in the context of sort of post-processing.
Ah, okay.
You like using this in the context of regression means like you're conditioning on the design matrix, right?
Yeah.
Right, but in the context of sort of post-processing the output of a differentially private algorithm, you don't have the design matrix sitting there. It's sort of behind the, you don't have direct access to it. So anyway, it's fine.
So okay,
I'll ask another question later.
Yeah, it's true. It's true that when it comes to privacy, then you need the matrix, the X's. Yeah. That's true. You would need the X's, and so in that case, you would be assuming that those X's you can share. But of course, that's not necessarily the case. So for the moment, so these are, as I said, I'm new to privacy, so these are limitations that I'm conscious of. But there can be, for example, you can assume a generative model for and it can only be approximate for your X's. You just say give a distribution for each of the X's and a joint, and you can do this, and you can correct in case the user wants to say, okay, I don't think this X was exponential or Gaussian. I'm going to find the parameter of that X by changing that. But it's true, that's a limitation. Yeah. Any other questions? Okay, well, I'll just skip. I'll just rapidly go to the simulations. So it's a very simple setting. We want to, our score function is the score function for the location parameter. And so we want to estimate the mean of a distribution. And then we use the Huber function as a row function, so the bounded function we saw earlier. And another idea is although the limitation is specifying a full generative model, what it does is that by choosing this tuning constant k, you don't have to bound the parameter space. In many cases, you don't have to bound the parameter space nor the data. So you're not truncating the data. And so we want to see the impact of this tuning constant when it comes to statistical accuracy of the differentially private output. So we just use, idea is, okay, can a robust mechanism with bias correction be used within existing differential privacy mechanisms, and can it improve statistical accuracy? So we just use objective perturbation as as a privacy mechanism, and so I'm not sure. I'm guessing everyone is aware of it, so I won't go through it. So we use this, and we just consider a simple setting where in all cases we assume sigma is known, although as in previous talk we can extend it to the place estimating sigma. But for all cases we assume sigma is known, and we have a sample mean of 3. We have different sample sizes of 100 and 1000, and 3 levels of privacy budget. And we make this tuning constant vary between 0.5 and 2, which is the range usually defined for the tuning constant of a Huber function. So these are commonly known, and so we're just studying what the range is for this problem. Okay, so we compare, in order to say, okay, how good are these privacy mechanisms with respect to the underlying estimator we want. So we use as reference the sample mean, okay, so, and the robust mean. So in this case, the robust mean is not biased because it's symmetric, the normal is symmetric. And then we have 5 different, it's 6 different kind of objective perturbation mechanisms. So the first 4 are based on truncating my data in order to have these perturbation mechanism or parameters. So we have different forms of truncation, quite good truncation, so we're around the mean, precisely around the mean, in a good vicinity of it, a very large one, and then small bias truncations on one side or the other. And then we have objective perturbation applied to directly to the robust estimator with the Huber psi function. And then we have the bias corrected robust one. Because this one, when you perturb it, is biased, and therefore we apply the iterative bootstrap to correct for that bias. Okay. So just one additional thing, we have in various simulations we had different points that were quite lying outside, so we decided to use a robust measure of the mean squared error based on the median and the median absolute deviation. Okay, so what do we see here? So I used the log of the mean squared error because the distances were otherwise squashing everything together. So what we see here is the blue line is the mean squared error of the sample mean. Okay, and as we expect, it should be performing very well. Okay, the robust estimator. This is, I forgot to say, sample size equals 100 and privacy budget 0.1. So the robust estimator also lies pretty close to it. There is an advantage of the robust estimator when the model is correctly specified, meaning that it's cutting off observations where they become more variable, and therefore it can improve in terms of mean squared error. And then here, these constant lines, of course, on the x-axis we see the k, the tuning constant, that we make vary between 0.5 and 2 for robustness. So the only ones that are supposed to change with this tuning constant are the robust one, this brown line, which is the perturbed robust one, and this one being the bias corrected robust one. Okay. The other lines you see here are the other 4 objective perturbation methods. Okay, so what we see, at least for epsilon equals 0.1, the tuning constant k, as this increases, it starts going back up. But in any case, we're lying below, in terms of statistical accuracy, it's improving over most of the range of k. Same thing for epsilon 1, where now we're going up. So they're all improving, of course, because the privacy budget has gone down. And here we see that it's going back up, but not as steeply as before. And when epsilon equals 2, it's still going down here. So I'm assuming I didn't try it, but as k goes on, it'll go on further up later. So there's a kind of trade-off between the epsilon privacy budget and the k. But in any case, we're doing better than the the best possible truncation we have. Okay. So, well, there's same message for sample sizes equal 1,000. So that's I'll basically just skip those and go to the conclusion. So basically, what we see is that despite the tuning constant having a range, we can manage to keep, well, at least in this very simple simulation setting, we can perform at least as well as the best truncation on the data without and being very flexible on the K. And that allows us to, and this framework allows us to avoid putting arbitrary truncations on the data, which can lead to possible problems with inference. There is a role that can be played and can be studied between the tuning parameter K and the privacy budget epsilon. Okay, so that can be studied, and so we can understand the trade-off between utility and privacy based on this relationship. These simulations were also made on defining the exponential distribution with similar conclusions. So the limitations, as we were discussing earlier, it needs a fully parameterized setting and a well-defined score function whose expectation is 0. And the tuning constant K can also depend on the scale of my problem. So I'm assuming there's less assumptions to be made on the scale of the problem rather than the range of my data. And we still need to, if the routines such as iteratively reweighted least squares can be used in a private manner. And so we're looking into the exponential mechanisms using Tukey byweight function, and this has possibly got some good results there. And so the direction is to see these correction and inference mechanisms, how they can be applied directly to differentially private outputs, and understand how robustness can be used within already other existing differentially private mechanisms. So yeah, that's it. Thank you very much.
So we maybe have time for one question.
Yeah.
So the Hoover function is not second order differentiable.
Yes.
But to apply objective perturbation, you need a Hessian to have a larger second value to be dependent.
So it doesn't have. So to my knowledge, for objective perturbation, it doesn't. It needs to be almost everywhere differentiable.
Oh yeah. So you need a gradient Lipschitz constant. Okay.
So it should be okay.
Okay, so you might take any other questions to the break. Let's thank Roberto again.
Thank you.